Hello Year 12, this is the audio feedback on your materials assessment. How Frog works is when we set a quiz as an exam, you cannot know which individual questions went wrong, and because of that we can't give individual feedback to the students. So what we have decided is to give you feedback on all the 20 questions in the assessment, and then hopefully you would remember what you have marked in your test or what you have chosen as a particular answer in your test, and then you can compare and take proper feedback from that. So we are moving on to the first question. Now another thing about Frog is for each student it randomly selects the question, so the order of the questions will not be the same for all of you. So I'm just going in one particular order. Some may have done in this order, some may have not, but still you will have all your 20 questions here. So first question, what is the name given to a material that breaks without deformation when a force is applied? So here the key word is it breaks immediately after the elastic limit. There is no deformation. It doesn't go, there is no deformation means it doesn't go to plastic. And we have only one type of material that behaves in that way, and that is brittle. So the answer for this particular question is brittle. Okay, so we are moving on to the next one. So now the second question. So you have the question there. So what are the key things or the key information in the question? They have given us the total spring constant as 15 Newton per meter. They are asking us to find the energy stored. So whenever we see a spring and the energy stored comes into the picture, the equation that should come to our mind is half force times extension. But now when we look into the question, we don't have extension with us, but we know the spring constant and the force. So Hooke's law has given us an equation connecting force, spring constant and extension. So if we use that, we know that extension is force over the spring constant. Here it is, the spring constant is 15 Newton per meter for the total system. So it's for the combination. So the extension will be 3, which is a force divided by the extension, and you get the answer there. Once you have that particular answer, you know half is a constant, you know the force, you know the extension. Now you can plug it into the equation and you get the answer as 0.3 joules. Question 3, which cannot be used as a unit for Young modulus? So read the question carefully. Which or what cannot? So they are asking you what is not an unit for the Young modulus. We already know that Newton per meter square and Pascal both are units for Young modulus. So we have to choose between C and D. So C and D, you can see that they are completely in base units. So if we split our popular units of Newton per meter square into base units, we should be able to see which is the right one. So Newton, as you all know, is kilogram meter per second square. So you can find out what Newton per meter square is, and you can see that it is kilogram meter raised to minus 1, second raised to minus 2, which is our D. So that tells us that A, B and D are units of Young modulus. So our answer has to be C. Question 4. A sample of wire has a Young modulus E. A second sample of wire made from an identical material has 3 times the length and half the diameter of the first sample. What is the Young modulus of the second sample in terms of E? I just love this question, because the first time I did this, I spent around 3 minutes trying to work out, and each time I got the answer as D, 12E. And then I look into the mark scheme and it says it's not. So I was like, why? Then when I read the question carefully again, an advice that I always give my students, read the question carefully. Then I told myself, read the question carefully, and there were 2 key words there. A second sample of wire made from an identical material. So if two wires are made from the same material, whatever difference they have in their length, in their width, it doesn't matter. They will have the same Young modulus. So the answer has to be B. So I might have really clever girls who would have already gone for B. If anyone else went for any other answer, this is a key thing there. They are made of identical materials, and identical materials have the same Young modulus. So you don't have to do any calculation here. So we have question number 5. A steel wire has a cross-sectional area 0.5 millimeter square. So keep in mind the units. It's not meter square. It is millimeter square there. They have given you the Young modulus. And the only extra bit here is they're telling you that the extension is 0.1% of the original length. That's only extra bit. Otherwise, everything is easy. So if you take the original length as L, extension is 0.001 times Ly, because it is 0.1%. So remember to divide it by 100. And then you know the equation for Young modulus. Rearrange it to find to make load or the force the subject of the equation. Plug in all the values that you know, and then you should get the answer as 100 newtons. Let's move on to question 6. The diagram shows the stress strain graph for two metal specimens X and Y. Which of the following is incorrect? That is a question, huh? Don't forget that. Which of the following is incorrect? So if you look, X is stiffer than Y. X is having a greater gradient, a bigger gradient, which means it has a greater Young modulus. So definitely it's going to be stiffer, because more the Young modulus, more stiff is going to be. So that sentence is correct. X has a higher value of Young modulus. Yes, that is also correct. X is more brittle than Y. If you look at X, it is going beyond the elastic limit. It is undergoing plastic deformation. Brittle materials don't undergo plastic deformation. So answer for that will be C. X is more brittle than Y. That is the incorrect statement. So question 7, they're asking you in which of the following relationships X and Y are inversely proportional. So if you look at the first one, energy and extension. Energy is equal to half times force times extension. So they are directly proportional. Gravitational field strength and distance. If you think about that equation, gravitational field strength is inversely proportional to 1 over r, or inversely proportional to r square, not just r. So it's not that also. Wavelength and momentum. You have studied de Broglie wavelength, where lambda is equal to h over momentum. So they are inversely proportional, and so the answer is C. So we are moving on to question 8. So you have question 8 there. Let's look at the key information given to you in the question. We have a parallel tube spring system. That is important. And the spring constant of each spring is 20 Newton per meter. Find the energy stored. Like one of the previous questions, the energy stored is again half force times extension. We know the force here, but again, like in that question, we don't know the extension. But we know the spring constant, so we can find the extension using a very similar method to the previous question where we have discussed the same thing. But the only difference here is they have given us the spring constant of each spring. So when you are going to find out the extension, you do force divided by spring constant. That is where the tricky bit comes. They have given you the spring constant of each spring. This is a parallel combination. So you need to first think, what is the parallel spring constant? What's the total spring constant for a parallel combination? Okay, and then you have to divide force by that. So you already know that in a parallel combination, The total spring constant is the sum of the individual spring constants. So the total here will be 40, extension will be 4 divided by 40, and then if you plug it back into the equation for energy, you will get the answer as 0.2 joules. Question 9, we have done a very similar question in one of our team's session. So what does the shaded area represent? Shaded area is the energy that goes as the internal energy of this material. So that is the energy that we don't get back. So it is the C, the energy per unit volume, which cannot be recovered. Let's move on to question 10. So we have quite a lot of information in this question. We have a wire of length L, W is that wire, radius R, and it hangs vertically and a load is attached to the bottom. It extends by E. We have another material X, or we have another wire X that is made from the same material, has the same load attached to it. In that case, what length and radius can produce an extension of E over 4? So when we think about the material, it is the same material, isn't it? So the Young modulus is going to be the same for both of them. What we have to find out is extension. So if you look at the equation for extension, you can see that it depends on 4 things: the load or the force, the length of the wires, then the area of cross section of the wire, and the Young modulus. Now, if you look at the information given, both the wires are of the same material, so the Young modulus is going to be the same. Same load is attached to them, so F is also going to be the same. So that tells us that there are 2 things on which the extension depends. So it depends on length and area, because force and Young modulus are the same. It's directly proportional to the length, and it is inversely proportional to the area, or it is inversely proportional to the square of the radius. Now if we look at each option and see what happens, if you look at A, it says the length becomes half, so the extension should also become half because they are directly proportional. Radius doubles, so square of that is 4, and it is inversely proportional. So option A, according to option A, the extension should go down by a factor of 1 over 8. So our answer is not that. If you look at B, length remains the same. Radius increases by a factor of 4. So the area would increase by a factor of 4 square, 16. So the extension should decrease by a factor of 16. So the final change is 1 over 16. Again, we don't want that. C, length doubles, so the extension should also double. Again, radius doubles, so area increases by a factor of 4. Extension should decrease by a factor of 4. So if you combine both the changes to length and radius, the total extension goes down by a factor of 2. Again, we don't want that. So obviously it leaves us only with one option, which is D, but we can check. So length increases by a factor of 4 means extension should increase by a factor of 4, and then radius increases by a factor of 4 means area increases by a factor of 16. So extension should decrease by a factor of 16. So if you combine both the changes, you can see the total change is 1 over 4, and that is what we want. So our answer for question 10 is D. Moving on to question 11. So a stone is projected. When each chord is extended by x, the stone is projected with a speed v. Assuming all the strain energy is transferred to the stone. So all the strain energy is going to what energy there? Is getting converted into kinetic energy. So what is the speed of the stone if the chord extends by 2x? So they are asking us to relate strain energy and kinetic energy. So you know that the equation for strain energy is half kx square, and here the equation for kinetic energy is half mv square. So half kx square gets converted into half mv square. K, half is constant anyway. K is a constant, M is a constant. So we can see that x square and v square are proportional to each other. So that tells us that x is proportional to v. So if x increases by a factor of 2, then speed v should also increase by a factor of 2. So our answer for question 11 is C. Question 12. So we have two strings of equal length, different thickness, same force, same material. One has a diameter of 0.2 millimeter, other has a diameter of 0.8 millimeter. So we have to work out the ratio of their potential energy. Now when we think about potential energy, the problem is the equation that we know is half times force times extension. But then the question tells us that the diameters are different, which means their areas are different. So we need to bring that into the equation. So when we look at the other data given to us, they're telling us it is the same material, which means the Young modulus is the same, but diameters are different or areas are different. So it is something to do with the Young modulus. So think about the equation for Young modulus. So it is force times length divided by area times extension. So if you look at this particular equation, both are the same material. So E is a constant. They are under the same tension. So F is a constant. Equal length. So L is a constant. The only thing that is changing is A and E. So that tells us that AE is a constant. The area of the thinner wire times the extension of that wire is equal to the area of the second wire times the extension of the second wire. Now, if you consider the areas given to you, so extension of the first or the thinner wire divided by the extension of the thicker wire. Now you can see that when you rearrange them, E1 over E2 is equal to A2 over A1. So it is the other way around. So you get 0.8 square divided by 0.2 square. Now you can ask me, but then those are 0.8 and 0.2 are the diameters, they are not the area. But then you have pi d square over 4 in the numerator and pi d square over 4 in the denominator. So pi and 4 gets cancelled. And what we are left with is diameter square. So now you know the value of E1 and E2. So you can put it back into the equation. Elastic potential energy of the thinner wire is half F times E1 and thicker wire is half F times E2. Half and F gets cancelled. What you're left is with E1 over E2, and that is 0.8 square divided by 0.2 square, and you get D16 as the answer. Moving on to question 13, they are investigating two wires of the same metal. So if the two wires are are of the same metal, then their Young modulus has to be the same, their force constant has to be the same. So if you look, the question is, which of the following statements are correct? So the first one is Young modulus is equal to the gradient of the stress against strain graph. Yes, definitely. Force constant is a gradient of force against extension graph. No doubt in that either. The graph of stress strain against stress and strain have different gradients, which means they should have different Young modulus, which is not true because they are the same metal, so they should have the same gradient as they have the same Young modulus. So the answer for this one is B, only 1 and 2. Question 14 is quite an easy one. You have the graph, 4 different materials there, greatest work done. So work done is the area under the graph. So it is quite obvious which line has the maximum area under the graph, and the answer is B. Question 15, you have again 4 materials there, and they are asking you 2 things here, so be careful about that. Which material is brittle and has the greatest ultimate tensile stress? So brittle means it should be only a straight line and nothing after that. So you can see that it is A and B. They have asked one more, they have put one more condition there. ultimate tensile strength. So that is B. Question 16 is another very easy question. They have given you the weight and they have told you what is the breaking stress, and they're asking you to find the cross-sectional area. So the equation that should come to your mind is the equation that connects stress, force and cross-sectional area. The only tricky bit here is the unit for stress. It is 130 kilopascal. So if you don't convert that into Pascal, you end up getting the wrong answer. Otherwise, your answer should be B, which is 6 times 10 to the power minus 5 meter square. Again, a very easy question. You have a 3 kilogram object suspended and the wire has a diameter of 0.62 millimeter. What is the stress? So this time, instead of weight, they have given you the mass. And all of you know how to convert mass into weight, multiply it by gravity, and to find stress you need area. Two things here, they have given you the diameter, don't forget that, and the unit is in millimeters. So if you do the right conversions, then you end up getting D as the answer. Question 18 is similar to one of the previous questions. You have two wires and you have to compare their extensions. They have the same length. The tension in each wire is the same, which means the force is the same. Both obey Hooke's law. What is the ratio of their extension? So again, you have to look at the equation for Young modulus. And if you make extension the subject of the equation, you can see that it is FL over A times the Young modulus. Force and the length are the same. So that tells you that extension is inversely proportional to the area and Young modulus. So the extension of X divided by extension of Y will be equal to Young modulus of Y times the area of Y divided by Young modulus of X times the area of X. So after the calculations, you will get D 3.3 as the answer. A very simple question towards the end of the paper, and as I said, some of you might have got this question in the beginning. So you have a spring and you're applying a force F on it. The energy stored in the spring is E. What is the extension? Can a question for A level be simpler than this one? No. The answer for that is X equals 2E over F. And to the last question, you have a graph which shows a variation of stress against strain. You have to calculate the Young modulus, which is very easy. It is a gradient of the straight line part of the graph. But there are two key things you have to keep in mind here. One, the unit of stress is in megapascals. So remember to convert that into pascals, and strain is in percentage. So you need to divide whatever is the value you're getting from the graph for strain by 100. So if you do the right conversions, you end up getting D as the answer. So this is how you arrive at the right answers for all the 20 questions in your assessment. I'm hoping all of my explanations have made sense to all of you. If still something is there somewhere which you can't digest, which you don't agree with me, please feel free to drop me an email and we can discuss and get that cleared. Okay? You will be getting a similar feedback for your quantum mechanics assessment also. Okay then, bye-bye.